इसका गीला हो गया तो जाएगा ना, गीला कैसे नहीं करते? अच्छा गीला करते हैं चिपका लेते हैं, गीला हो गया हाँ वो बिना गीला के नहीं चाहिए हाँ सप्लाई करवा के लगे ठीक ये बगल वाला और ये खुलवा है।
So good morning, everyone. Welcome to this webinar on the UI Assist webinar. So this is being done by the UI Assist team. Today we have Nilay. Nilay is from Washington State University. He's a PhD student there. He did his master's from IIT Kharagpur before joining Washington State University. So the first session will be taken by Nilay, and the second session will be by me. So my name is Srinath. I'm a PhD student at IIT Kanpur. So Nilay's topic would be optimization for optimal control in distribution power systems, and I'll be talking about GPS spoofing in power systems. So we'll start the meeting. So I'll hand over the mic to Nilay now. So
Hi everyone. Let me know if you can hear me well. Okay. So I'm doing a PhD under Dr. Anurag Srivastava at Washington State University, and I'm working on distributed optimization for voltage control. But I will talk in a more general form about optimal control in distribution power systems. So yeah, it's not taking the next slide. Okay. Okay, so I didn't know about I didn't know much about the audience here. So I mean, I think everyone is aware of this UI assist, and it's a 5-year project between US and India, and Washington State University is a US lead, and IIT Kanpur is the India lead. So I've been here in IIT Kanpur for the last 5 days, and I've been collaborating. I mean, I've been talking and discussing with professors and students here, and then also looking into future collaborations if possible. So UISS is mainly on modernization of distribution power systems, like in terms of control, in terms of communication, and also looking into how robust we can make it. So these are the contents of my presentation. I'll talk more about the AC optimal power flow problem, what non-convexity means, what is NP hardness. Then I'll look into relaxations and approximations, and then I'll talk briefly about the centralized approach for optimal control, and then how can we shift towards a more distributed control or a more distributed approach. So this is a very basic AC optimal power flow problem or ACOPF problem. So the variables that we have are voltages, both in magnitudes and in the bus angles, and also power injections. We normally try to minimize the generation cost, and then we have power flow equations that we have to maintain, and then there are some operational constraints like voltage constraints, generation bounds, and thermal limits, and then angle limits. So the angle limits is the only thing that we try to avoid in distribution systems, particularly in radial distribution systems, because once it becomes radial, then angle relaxation can be done very easily, because once you formulate the distribution system power system model neglecting the angle limits, we can easily trace back the voltage magnitudes and then angles. So in transmission systems, normally we have all the power flow equations and then the different operational constraints. So the thing here is that even 50 years after the problem is formulated, it's still an open-ended problem, because there is no fast and robust solution technique to solve this full ACOPF. So in this ACOPF problem, what I mean by the feasible space is, so we have 3 things. One is the objective, which we try to minimize. We have a set of operational constraints, and we have a set of power flow equations. So the set of power flow equations along with the operational constraints, we are denoting this whole space as the feasible space of the ACOPF problem. So, and what has been seen in literature is that this problem is very non-convex, and which makes the solution of this problem to be NP hard. By NP hard, we mean that whenever you try to solve a problem, and as the size of the problem increases, then the computational difficulty that you face grows on exponentially. So
लेकिन ये चल नहीं रहा है, ये देखिए ये किन कनेक्ट हो रहा है.
Hello, excuse me. Can you hear me?
Hello.
Hello.
Hello. Hi. Yes.
Hello. Yeah. Do you have any question about this?
No, sir. Continue, sir.
Okay. Thank you. Yeah. So there are already some examples of this non-convex feasible space in literature. I have just shown a few examples of this. So there are some papers which shows that there is a hole in the feasible space. That means the feasible space of the ACOPF problem is not full. If there is a hole in the space, then obviously you don't know whether where to start with, where to have your own initial conditions. So if there is a hole and if there is a cut in the feasible space, then depending on your initial point that you start your algorithm with, you may end up in different local optimal points, and it will never be a global optima of the whole solution. And if the feasible space is also disconnected, then it's the same thing, like you'll have many local optima for the problem. And then what it will result in is that the solution that you will get is not the global optimum solution of the problem. Hello. So researchers have come up with two things to solve a non-convex ACOPF problem. One is called convex relaxations. So what researchers do is that they expand the AC feasible space of the problem. And then if you see on the right hand side, so this is a very non-convex AC space, which is shown by this yellow yellow field space. And then what researchers do is that they expand this whole space in such a way that the relaxed space becomes convex. Now once this relaxed space becomes convex, then what it helps is that you can reach a global optimal point using any polynomial type algorithm. And so to start with, we have the original non-convex ACOPF problem. Then we use some kind of convex relaxation. Then we use some kind of convex relaxation. Then what happens that the primal problem becomes a convex problem. But the thing here is that we have to maintain zero relaxation gap. What this relaxation gap means is, if you see in this figure, so we have this AC space. Suppose we have relaxed it by this red circle. So this is the relaxed AC space by this red line. And then the minimum amount of relaxation that you can have on this AC space is this dotted line, which has an objective value of AC star. And the relaxed line has an objective value of R star. So once you relax it, what you have to check is the optimal solution obtained from that relaxed problem and the optimal solution of the original ACOPF problem should be same. If there is a difference between these objective values, then what happens is that whatever you get is not the original optimal solution. So this difference is called the relaxation gap. So once you have the non-convex ACOPF problem, you relax it, get the convex primal problem, then it becomes easy. Then you can convert it to a dual problem using some duality, zero duality, maintaining zero duality gaps, and there are sufficient, like there are many theorems on that. So once you get the convex ACOPF dual problem, then you can solve it by any polynomial type algorithm. But the catch here is that, again, you have to check whether the solution that you got is AC feasible or not. That means whether it lies in that original AC feasible space or not. If it doesn't happen, if it doesn't fall within that AC feasible space, then whatever you got is not the right solution. So in terms of power systems, what we have to do is that we have to convert the original non-convex primal problem to a convex ACOPF dual problem, and then find a solution. And by finding a solution means we have to find the voltage magnitudes, the bus voltage angles, and the power injections of each node. So, and the next thing that researchers look into are approximations. So what approximations mean is that, suppose we have the same original AC space, then as you know that the power flow equations in the original ACOPF problem are non-linear, right? So somehow you use some kind of approximations, like for example, we have DC approximation, we can linearize the whole power system equations around a certain operating point. So using different type of approximations, what we are doing is that we are making the original non-linear, non-convex power flow equations into a set of convex equations. So as you can see, so this is a convex AC space, right, on the right hand side by this, which is given by this yellow space. Now once you approximate certain variables or certain points, then what happens that the AC space shrinks at certain points, and then this is a very basic or a typical example of an approximated ACOPF space. Now, once you get the approximated ACOPF problem formulation, which is convex, you solve it. And then the solution that you get, you have to trace it back to the original voltage magnitudes and bus angles and check whether it is physically realizable or not. If it is not physically realizable, then obviously you have to look into other ways. But the main thing of all relaxations and approximations is that you somehow make the non-convex ACOPF problem into a convex problem, solve it, and then you check if the solution that you got is AC feasible or not, or if it is physically realizable or not. So this is a very basic. So what I'm doing now is in my thesis work is I'm looking into optimal voltage control in distribution systems, and I'm using branch flow model. So there are two types of models to represent power flow equations in distribution systems. One is the branch flow model, and the other one is the bus injection model. The main advantage that branch flow model gives is that since distribution systems are mostly radial, branch flow models give a much easier representation of power flow equations. And so here I have shown the whole problem in a branch flow model. And this is centralized optimal voltage control problem formulation. So I'm minimizing the voltage deviation of each nodes from a reference voltage, and the power flow equations are written like this. So Lij is basically the matrix, because once you go to an unbalanced distribution system, you have all three phases coming up, right? So you have Iij, phi ij. So phi ij is basically composed of both A, B, C, or both three phases. All the three phases. So Iij, phi ij basically means current in phase A, current in phase B, and current in phase C. So Iij, phi ij in the first equation is basically a 3x1 matrix, and Iij, phi ij Hermitian will be a 1x3 matrix. So basically Lij will be a 3x3 matrix, and it becomes 3x3 because we are now dealing with a distributed, we are now dealing with unbalanced three-phase distribution systems. If it had been a single-phase distribution system, Lij will be just a 1x1 variable. Similarly, voltage will also be, Vi will also be a 3x3 matrix. And then we have a voltage drop equation, we have nodal conservation of power. By nodal conservation of power, I mean that suppose there is a line from I to J. Suppose there is a distribution line from I to J. So the power which is flowing from I to J is basically the summation, which is summation of all the power which is going from J to other lateral branches, and the addition of demands on node J. So nodal conservation of power maintains the Kirchhoff's nodal power laws. And then we have this equation, Pij square plus Qij square is equal to voltage into current square. And so as researchers have seen, so as you can see, like all these equations are kind of convex, like the voltage drop equation is convex, the nodal conservation power is convex, but the only non-convexity that comes up in this set of equations is this equation, this Pij square plus Qij square is equal to voltage into current square. So what researchers do is that they kind of relax it. They relax it in such a way that they use this inequality, which is known as the second order conic relaxation inequality. So if we use this second order conic relaxation or SOCP or SOCR, then it becomes a second order conic programming problem. And then you have all these bounds, you have all these constant equations, like on voltage, you have constants on active power, reactive power, and also on thermal limits. So ultimately, this whole set of equations have convex equations, which are voltage drop and nodal conservation of power. Then this set of constants also are convex. And then the only non-convex equation that we had, we have converted to an SOCP relaxation. So this whole problem formulation now becomes a convex formulation. Then we can move towards dual problems, like we can convert it to a dual problem and then we can solve it. So if you see in this diagram, what happens in practical or in the real physical field is that we have capacitor banks, we have energy storage systems, we have tap changers and voltage regulators. So what I mean by centralized voltage control is that, so the DMS or the distribution management system is responsible for maintaining voltage throughout the feeder, right? So we have this volt var control scheme, which measures, which takes in all the measurements throughout the distribution feeder. It can be the voltage at different buses, it can be power, or it can be current at different positions of the power system network. And then it runs this optimization problem. It runs this branch flow model problem. And then whatever optimal solutions it gets, the optimal solutions will be in terms of how much of tap settings we should set, or how much of active or reactive power injection that should come from an energy storage device, or what should be the status of capacitor banks at different positions of the network. So all these commands are then sent back to those particular devices, and then ultimately voltage is maintained throughout the feeder. So this whole problem formulation in the branch flow model can be ultimately expressed in a very simplistic way by this set of equations. So the variables that we have are Pij, Qij. Pij means is the branch active power flow from node I to node j. Similarly, Qij is the reactive power flow. Lij is the current square term from coming from I to j. Pgi, Eli are the generation and loads at node I. Similarly, Qgi, Qli, and voltages. So all these variables is represented in a set, and this is represented in form of y, and then we are minimizing fy. It can be minimizing generation cost, it can be minimizing power system losses, or it can be minimizing voltage deviation, as I have shown here. So fy is basically minimizing that objective that you want to minimize, and subject to gy equal to 0. So G represents the matrix, Gy equal to 0 is the equation which shows all the power flow equations that we have. And Hy less than equal to Bm, this shows the operational constants like voltage bounds, active and reactive power bounds, then thermal limits and everything. So G represents the set of power flow equations, and Hy less than equal to Bm, this represents the operational constant equations. So this is a very basic centralized optimization problem in distribution systems, written in a very simplistic way. Now let's go to distributed. So once we go to distributed, we have to see how it differs from the centralized one. So what what people normally do is that let's divide the objective, the set of powerful equations, the set of operational constraint equations into subregion based equations. So suppose you have the whole power system network, and then you divide the network into three subregions, subregion 1, 2 and 3. Now as you can see, variables AK means K is the number of subregions that you have. So K is basically equal to 3 here. So AK, suppose in subregion 1 you have all this set of variables, Pij, Qij, Lij and everything. And similarly in each of the subregions you have all these variables, and then you represent the centralized objective Fy in terms of subregion based objectives. So K is 3 here, so basically it will be like F1 of A1 plus F2 of A2 plus F3 of A3. So the objective now becomes a summation of all the atomic or all the subregion based variables. Similarly, Gk Ak is equal to 0k here. So basically I have decomposed, or I have disintegrated the original centralized power flow set of equations, the set of powerful equations, into subregion based powerful equations. Similarly, subregion based operational constants. The only thing that we add here is the coordination matrix. So why do you need this coordination matrix? We need this coordination matrix because suppose you divide the power system network into different subregions, and then the only communication that those subregions should have is the periphery end voltages or the periphery end power flows that are going to happen, right? So AK, capital AK, small ak will represent all the coordination that is happening between two neighboring subregions. It will be in terms of, so the voltage in subregion 3 will have some relation with voltage in subregion 1. Voltage in subregion 3 will have some relationship with voltage of subregion 2. So all these things are represented in this coordination matrix. Now, once you divide objective, set of powerful equations, set of operational constraints into subregion based equations, then it becomes a distributed optimization problem. Now you use any kind of distributed optimization algorithm. It can be ADMM, it can be any other algorithms, and then try to solve it. So in conclusion, what I will say is, so the original ACOPF problem is a twofold problem. You have to use relaxations or approximations to make the original ACOPF problem a convex problem. Then you divide the whole power system network into certain subregions and represent objectives as well as all the equations into subregion based objectives and equations, and use any algorithm to solve the whole problem. And once you solve the problem, you have to check that the optimal solution that you get is really lies within the feasible AC space of the power system network. That means you have to check that from the solution you can trace back the bus voltage magnitudes as well as its angles and the power injections in each of the buses. And the challenges that we have is that the feasible space is non-convex, and then we have mutual coupling in distribution systems which make problem formulation difficult. We have regulators and capacitors which incorporate integer constants, and hence problem formulation and solving becomes a little hard. Then the loads are also voltage dependent. Once the loads are voltage dependent, that the representation of loads becomes a little bit difficult to do that. And then the last thing is scalability issue of distributed optimization techniques. By scalability, what I mean is that suppose you find a solution for a 10 bus problem. Now, as you increase the number of buses in the problem, you have to check that the solution time to solve the whole problem doesn't go exponentially high. So this is, so your distributed optimization technique should be scalable too. Oh, thank you. I mean, so this is the end of my presentation, and I thank you for your time and patience on this. Yeah, thanks. And if you have any questions, you can ask me. Otherwise, I'll hand this to Srinath. Srinath is going to present next. Do you have any questions on this?
So good morning, everyone. So I'll be presenting a small discussion on this the GPS spoofing attack in power systems. So yeah, so real-time spoofing of the Synchrophasor GPS clock. So what exactly happens in a PMU is connected through, as you can see in this particular figure, you have a satellite, the GPS satellite. The PMU gets its timing information from this particular satellite, the GPS information. So what happens basically is the satellite sends the timing information. You have a clock, a GPS receiver clock. So this particular clock generates a signal known as an IRIG-B signal, an inter-range instrumentation group code. So IRIG-B code, as you can see here, is being used in this particular case for PMUs. So what happens? I mean, as soon as the data comes in, the IRIG-B code is used for the timing information, for the correct timing information for the PMUs. And this particular information is what is that you get with the data, the timestamped information. So this can be spoofed. So what generally happens is this particular information, the timing information, if someone is able to play with it, they can spoof the information. So this has certain implications in your real-life applications as well as in power systems. So in your normal GPS receiver clocks that you have in your mobile phones or your GPS receivers that you find in various your vehicles and all. So those can be even those can be spoofed. So your navigation can go off track. So that is one problem. And when it comes to power systems, what happens is as the timing information gets affected, the phase angle measurement that gets deviated. I mean, it won't report the correct the phase angle measurements. So we tried to simulate a similar thing here just to study a few scenarios. So the setup that we had used is what you can see in this particular figure. So we have two PMUs over here, an arbiter PMU and an SEL PMU. So the hardware setup that we had used is an RTDS, the real-time digital simulator, where we simulated the power system. So there are two experiments that we have done. The first one is on a WSU 9-bus system where we studied the impact of the GPS spoofing attack on Synchrophasor assisted load shedding. So there was an adaptive load shedding simulation created. And the second case is like how the GPS spoofing attack would impact state estimation, the performance of a state estimator. So for that, we use this RTDS. So the RTDS is where the model was simulated. So there are two particular systems modeled. One is the WSU 9-bus system for the load shedding scheme, and IEEE 30-bus system to study the impact on the state estimator scheme. So what we did here is using two PMUs, as you can see. This is the arbiter PMU and the SEL PMU. So the arbiter PMU generates it has an arbiter clock that is a GPS or a GPS clock. In fact, so that generates an IRIG-B signal. So this GTDI card, that is the gigatransceiver digital interface card, is something that sends the information to the RTDS. So inside the RTDS, we created a delay block, something known as a delay block, where we create a spoofing signal. So that particular delay block creates the, as you can see here, this is a spoofed signal that comes out of it. So to get this information, we used a GTDO card, a digital output card, and that particular IRIG-B signal is then fed to the SEL PMU. So now this particular PMU gives you the correct information. This is the correct time signal, and here this gives you a delayed signal. So as explained here, we are using two hardware PMUs which provide realistic synchrophasor measurements as per the industrial standards. We have also used this particular RTDS has software PMUs. All right, so the software PMUs again synchronized to the external 1 PPS IRIG-B signal, but we didn't spoof any of them. So those software PMUs were used to measure the voltage phases at certain buses in the power system, the simulated power system, in fact. So generation of the IRIG-B spoof signal. So as you can see here, the hardware PMUs, PMU A, which is time synchronized, and the time spoof PMU B were deployed at the reference bus of the, okay. So this talks about the state estimator algorithm. As I'll go further, I'll discuss that further. So what happens here is you have this desktop. This is the RTDS. So we use a software called as RSCAD. So this RSCAD acts as the graphical user interface for the RTDS. So this is where you create your power system models. It's similar to the PSCAD. And this is the GPS clock. So from the satellite, this gets the information to the GPS clock. Power amplifiers are used, and this information is then fed to the PMU A. That is the R-byter PMU, which is not spoofed in this particular case. Now, what you do is the IRIG-B signal that you get from here, you take it out, you create a delay through the RTDS. Let me explain this also. Like, you don't need an RTDS to create a delay. In fact, if you can use a normal DSP blocks to create a time delay, so it becomes a total hardware setup. So here we have used a small software thing. So the PMU A, the delayed signal comes to this spoofed the PMU B, SEL PMU, and this information is then sent to a router, and it goes to something known as a phasor data concentrator. So we are using OpenPDC for this particular case. So in OpenPDC, the data is stored, and the data is time streamed, and this particular data is stored into a database. So which is in this particular PC, and this can be used for various applications. So in this particular case, we are showing a state estimator application. It can be state estimator, a synchrophasor assisted load shedding, multiple schemes, anything that can be affected. This can be studied. So this gives you a representation of what is happening. The oscilloscope screenshot of the pulse PPS signal, time aligned with reference, and the spoofed IRIG-B signal to induce error equivalent to 1.6 milliseconds. So this is the error that we have created. So as you can see, this is the reference IRIG-B signal, the yellow one, and the green one is the spoofed one. So there is we create a small delay of 1.6 milliseconds. So how much this would affect the phase angle measurement can be seen as we go further. So the physical setup that we are using is a PMU model 1133A power channel of R-byter systems, which is used to generate the IRIG-B time code. As I said earlier, IRIG-B time code is obtained from the first PMU, the R-byter PMU. Well, this model, as I said before, is equipped with a built-in GPS satellite receiver. And this particular receiver is what is used to create the time clock. I mean, the GPS time clock. It has an inbuilt GPS time clock. It can also be used to transmit the time code output to synchronize other substation equipment. So that is what the R-byter entire PMU setup does. So the time code signal that is generated using the R-byter PMU, that is sent to the, as I said before, to the PMUs, to the RTDS. The RTDS, which has a delay block. Okay, so this delay block is used to manipulate the time signal in real time. And this particular information is again then fed back to the SEL PMU, which is the spoofed PMU. So here you generate the signal, and here the original IRIG-B signal, the unspoofed one in the R-byter PMU, which has an inbuilt synchrophasor clock or a GPS clock, and the PMU B signal, which receives the IRIG-B, spoofed IRIG-B signal from the R-byter PMU. So here we take the first scenario. Here we consider a GPS spoofing attack. So here what we study is the impact of GPS spoofing on synchrophasor assisted load shedding. So load shedding can be of three types. So you have the traditional schemes where the load shedding is entirely based on the frequency deviation. So you have frequency deviation. So based on how much the frequency deviation, you decide how much load to be shed, such that the frequency gets back to the normal value. In the second scenario, you have a semi-adaptive scheme. So there you use frequency and rate of change of frequency to determine how much load needs to be shed. And third is like you have a adaptive scheme. So in the adaptive scheme, the frequency, rate of change of frequency are calculated, and we do it at a central inertial center. Okay, so it is a centralized scheme. So it goes to a central place. So it decides what load needs to be shed, and that calculation happens. So it uses a synchrophasor based, the frequency and the rate of change of frequency measurements are obtained using PMUs, in fact. So that is what, here we study the impact of the synchrophasor, the GPS spoofing attack on synchrophasor assisted load shedding. So what happens is the WSEC 9-bus system is what is used to study this particular scenario. So the attack is created, this is simulated on RTDS, the WSEC 9-bus system. You have multiple PMUs connected. So you create an attack scenario. So what happens when you create an attack is the phase angle measurements get affected. The phase angle measurement also affects the frequency and rate of change of frequency measurements. So this frequency and rate of change of frequency measurement is used to determine how much load needs to be shed. Okay, and the trigger for the load shedding model based on the system, this is SFR model is known as a system frequency response model. So that is what we use in the adaptive scheme to determine the load to be shed. And the loads are shed at this particular thing. That is determined using MATLAB or an external software. And this external software sends the information back to the RTDS, like how much load needs to be shed. And based on the incoming information, the RTDS triggers the load shedding scheme. So this is what happens. So the system frequency, the mathematics behind it, the system frequency and the rate of change of frequency are estimated from the phase angle vector. So the phase angle vector, it's basically a simple least square algorithm that you use here. So if this is your, so this is your state vector, x0, x1, and x2. You have 3 states. Your first state is the initial angle. Your second state is the frequency deviation. And your third state is the rate of change of frequency. Initial phase angle, the frequency deviation, and the rate of change of frequency. So the x can be calculated using a least square algorithm. So this is your state. This is the unknown. Phase angle you can obtain by using any sampling technique. And then you have the least square algorithm. Equation 1 is a least square algorithm, where the metric C is in fact based on delta T is the time sampling, is the sampling interval of the phasor estimates. So you obtain a series of time samples. The series of samples are collected. Like let's say for every delta T, you run up to time T seconds. All right, or T seconds or T samples is what you collect at delta T sampling rate. And you obtain the metrics, the metric H metric or the C metrics, in fact, in this particular case, and use this particular equation to estimate the states, which are again the initial phase angle, the frequency deviation, and the rate of change of frequency. Now, what happens in this particular case is the phase angle, if a GPS spoofing attack is created, your phase angle gets affected. There's a phase angle error that happens. So in this particular case, what you get is you have this E5. So this phase angle error is related to your the attack. So let TU be the post attack, and TU star is the pre-attack receiver clock offset values. All right. So this is after the attack TU, and TU star was the original. So there is a time difference now. And let 60 be your system frequency. We have considered a 60 Hertz system in this particular case. So you get 60 and 360 degrees. So for every particular so for every particular time instant, what you get is there's a phase angle error that you get. So yeah, so this is your phase angle error. The phase angle vector after the spoofing attack, it looks something like this. So phi 0 dash is the phase angle vector, and phi 0 epsilon phi naught, these are the errors that you get. So phi 0 dash is in fact phi 0 plus the epsilon phi 0, which is the error that you created. Then from this, you use this particular vector to calculate the rate of change of frequency and the rock off. Switch. The frequency deviation and the rate of change of frequency are impacted by the erroneous phase angle vector. So this is your erroneous phase angle vector. You use this particular erroneous phase angle vector to estimate the states. So now what you're getting, this information that you get here is actually the correct rate of change of frequency measurement and the frequency measurement. So this was the experimental result that we had obtained. So as you can see here, the original measurement is this one, the red line, and we create there was a small fault created at this particular. There's a load shed. I mean, not load shed. There was a small fault created at 2 seconds, and the threshold was set at 59.5 hertz. So once the frequency deviation crosses 59.5 hertz, frequency falls below 59.5 hertz, a load shedding scheme needs to be implemented. So the frequency at the inertial center is what you see here. So the red line is actually without the spoofing, and once the fault has occurred, what we do is we create a spoofing attack at this particular time instant, and that causes a deviation in the frequency measurement. So as you can see, there's a small deviation in the frequency measurement. So in this particular case, the threshold is reached at this particular instant, time tr, and in this particular case, it reaches at tr spoofed. I mean, as you can see, there's a small delay in the particular time. So initially, it should have been shed here, but now what happens? The power shed, the load shedding happens at this particular time instant. There's a small delay. Yeah, so this is further explained here. So in this particular case, the blue line indicates without spoofing and without load shedding. All right. So if there was no spoofed signal and no load shedding, your frequency would have fallen like this. Now the black line is without spoofing and with load shedding. So if it was without spoofing, as you can see at red line, there's a fault created, the frequency starts falling. At 59.5 hertz, you would have triggered you have shed the loads. And that particular load shedding would have taken your frequency back to the nominal value, that's 60 hertz. Now, once you spoof it, what happens is your load to be shed, it should have happened here, but now it happens instead of TR, it happens at TR spoof. So it happens over here, and the frequency never gets back to the nominal value. It hovers around the 58 hertz value. So that is what happens in this particular scenario. So as you can see, in case of the GPS spoofing attack, there's a small deviation in the frequency measurement. So these are the values that we had obtained. So without spoofing, your trigger time should have been 2.667 seconds. But with spoofing, this was changed to 3.9. There was a delay of close to 1.3 seconds. And the power imbalance calculations also gets affected. So without spoofing, the load shed was actually 87.5 megawatt. But with spoofing, it turned out to be 66 megawatts. So it's actually it should have been 87.5, which would have taken your frequency back to your nominal value. But in this particular case, since only 66 megawatt is shed, it never returns to the nominal value. Now we study one more case here. So in this particular scenario, we study something known as the GPS spoofing attack in state estimation. So what happens in state estimation is, so in a state estimator, you get the measurements from the field, the raw measurements. So what are your system states in a power system? So power system states are basically your voltage, magnitude, and voltage angle at any particular bus. So these measurements are not directly measurable from the field. Well, with PMUs you can do it, but it's still in its infancy and hasn't been deployed to a very large scale. So what happens is you use the field measurements, which include traditional SCADA systems, which include the voltage magnitude, the real power measurement, the reactive power measurements, current measurements, in fact. Yeah. So all of them combined, you get it into the field to an energy center or a control center, where you run an algorithm, any algorithm. Basically, the traditional systems use the WLS algorithm or the weighted least square algorithm. Well, modern systems have started using Kalman filter-based algorithms, which are actually they're typically classified as forecasting aided state estimators, the Kalman filter algorithms, because there's a small prediction step involved. There's a small forecasting step involved in the entire calculation process. So here we study that particular case, the forecasting aided state estimator, the phase, which uses a Kalman filter algorithm. So here we have divided it. It's a hierarchical phase, asynchronous hierarchical phase algorithm that we consider. So I'm not going into detail on that. So this is pretty similar to what would have happened in a WLS scenario as well. Static state estimator or the typical wasted least square algorithm. So as you can see here, the blue is what is the true states. Now, what happens is your system states. All right, what happens? There is no validation of anything. Your system states with the spoofing attack. There's a considerable deviation, as you can see. That is what is shown with the yellow line. All right. So with the GPS spoofing attack, your phase angle. This is actually the angle measurement, state value radian at best end of the IEEE 30 bus system. So this particular bus measurement gets deviated. Now the control center has the wrong information, and this has certain implications. I mean, this would affect your measurements at your various control actions that is being taken at the control center. And I can include some validation schemes. So typical validation schemes include something known as a innovation or residual analysis. Well, these are statistical analysis techniques which can be used to detect bad data, like other anomalies in the power system state estimation process. So with some detection algorithms, so here I'm using a combination of innovation and residual analysis. So this is an algorithm-based technique. So using that, if you are able to detect the attack and remove the attack, they remove the bad data or the phase angle, in this particular case, the spoofed measurement, your system states can go back to the original values. All right. So this particular thing can be removed if you're using a detection algorithm. Now we also consider the simulation results. So this is the, as I said, we use a combination of residual analysis and innovation analysis. So as you can see here, this is the actually spoofed data. Okay, in this particular case, we are spoofing the measurement number 70, which is a PMU measurement. So that was the information that, so you can see a huge spike over there. So the system operator is able to identify that as a bad data, and that can be removed. And then further processing can be carried out. All right. So this is with bad data, and once you remove the bad data, your system goes back to the normal values, the red dots. And this is the normalized residual. All right. So innovation and residual, the difference is innovation is done using the forecasted values, and residual is done using, this is in a Kalman filter based algorithm, and residual is done once you have the actual states. So in this particular case also, as you can see, there are multiple spikes, which indicates it is a bad data, and you can remove it using some detection based technique, some detection technique. Okay, I'm using this algorithm based detection technique to remove the bad data. So this is how you can handle it. There are multiple applications which gets affected because of the GPS spoofing attack. So what we have done here is basically we have created a real-time setup where we can create a spoofing attack, and this particular information, the spoofed information, can be used to study the impact of GPS spoofing attack on various applications, not just state estimator and the Synchrophasor assisted load sharings. There are multiple applications that use actually the PMU data. So all these applications can be studied using this particular approach. And some detection algorithms have to be developed because this is cybersecurity is like it has to be implemented right at the grassroots level. So there should be some detection mechanism. So for the GPS spoofing attack, we haven't considered any detection mechanism. Whereas for the state estimation algorithm, we have considered a detection technique. So it can be handled quite effectively. So thank you so much for listening to me, for your time and patience. So if you have any questions, any doubts, we could take that up now. Any doubts, any questions? Yeah, so there's a question, how do you consider delay of receiving the hardware and software PMU signals in PC? Okay. There's a question actually, are bad data detection algorithms capable of detecting GPS spoofing attack? Well, yes, in fact, I mean, your phase angle measurements gets affected in this particular case. So using a normal bad data, the chi-square test or any other technique, like for a WLS algorithm, you can go for a chi-square test. And if it's a forecasting error state estimate, you can go for the conventional, the residual and innovation analysis based techniques can be used to detect the attack, in fact. So another question was, how do you consider delay of receiving the, how can we differentiate between a GPS spoofing attack and a false data injection attack? There's no particular algorithm. I mean, as of now, I don't know how it can be differentiated. The detection algorithms that we have right now, it will detect, it will tell you there is some attack happening. It won't classify between a GPS spoofing attack and a false data injection attack. Any other questions? All right. Is this attack happening in the physical layer? Yes, it can happen in the physical layer as well. I mean, basically what can be done is a PMU, if an adversary decides to bring a receiver. Okay, so what a PMU does is like it locks onto one particular signal, the GPS signal. Now, if you are able to create a signal with enough strength, so the PMU will think that the faked signal is the original signal, and it tries to lock onto that. So this has been implemented in various research papers. I mean, in various labs, people have done some research, and there have been GPS spoofing attacks that happened in your navigation systems also. So people have in fact done that. So yes, it happens at the physical layer. So what we have done here is, in this particular experiment, what we have done is it is done in a controlled environment in a lab, so as to study what happens, to study the impact and some detection techniques. That's what we have done here. Oh, there's one more question. How do you consider the delay of receiving the hardware and software PMU signals in PC contained in MATLAB software? So in this particular case, we don't consider that particular delay. If you go for a state estimation algorithm, the algorithm can be modified slightly. You can include some other techniques to consider this particular delay. There are estimation techniques that can be used to handle the delay in while using multi-rate measurements. In fact, PMU signals from multiple measurement from multiple sets. Can any communication delay be considered for the hardware PMU to be synchronized with RTDS? Well, we don't consider any time delay as of now. Basically, what happens is your PMU would give you the timestamp information whenever it is recorded. So this timestamp is actually your measurement. I mean, the timestamp is when it records the data. So this can be synchronized across locations, I believe. So communication delay, yeah, communication delay we do not consider. Any more questions? All right, so thank you for attending this particular session, the UI Assist webinar. So if you have any doubts or anything, you can drop an email or anything. I mean, you can, we'll share this particular, if you have recorded this session and it will be shared. So you can use it again. And if you have any doubts, you can like mail me or contact us. So thank you so much for your time and patience. And yeah, thank you.